Welcome to Next Gen AI. This lecture is brought to you by author, innovator, and technology leader Juan Achurra. With over 25 years of experience designing AI strategies, SRE frameworks, and enterprise platforms for Fortune 500 companies and government agencies, Juan brings the kind of knowledge most organizations pay thousands of dollars to access. So grab your drink, open your mind, and get ready for the flow of knowledge. Let's get started. Welcome. If you have ever been the engineer who gets paged at 3 in the morning because a production system is down, or if you want to become the engineer who prevents that from ever happening, this course is for you. I am going to take you through the complete foundation of site reliability engineering, and we are going to do it through the lens of modern AI-powered operations. By the end of this video, you will understand not just what SRE is, but why it exists, how it works, and where it is going. Let us get started. Here is what we are going to cover in this video. We will start with the origin story of SRE, why Google invented it, and what problem it was solving. We will move into the core principles and the 5-pillar focus areas that define the discipline. We will cover how to measure reliability using SLIs, SLOs, and error budgets. We will explore observability, the difference between monitoring and truly understanding your system. We will introduce AIOps and Generative AI and show you how they are transforming the role of the SRE. And we will close with the SRE maturity model, so you know exactly where your organization stands today and where it needs to go. This is a complete foundation. Everything that follows in this series builds on what you learn here. Let me start with the problem. Not a hypothetical problem, a real one that plays out in organizations every single day. A production system goes down. It is 3 in the morning. An engineer gets paged. They have no runbook. They have no clear ownership. They start manually digging through logs, restarting services, and hoping something works. Meanwhile, every minute of downtime is costing the business money. Research from Gartner puts the average cost of IT downtime at over $300,000 per hour. And for large enterprises, that number can exceed $5 million per hour. Hope is not a strategy. Reacting to failures after they happen is not engineering, it is firefighting. And that is exactly the problem that site reliability engineering was designed to solve. Let us look at where it came from. In 2003, Google had a problem. Their systems were growing faster than their ability to operate them reliably. The traditional approach, hire more operations staff, write more runbooks, respond faster to alerts, was not scaling. So an engineer named Ben Sloss proposed something radical. He said, what if we treat operations as a software engineering problem? What if we apply the same rigor, the same automation, the same measurement discipline to reliability that we apply to building software? That idea became site reliability engineering. Sloss defined it simply. SRE is what happens when you ask a software engineer to design an operations function. The result is a discipline that uses engineering to build and run reliable systems at scale, not by hiring more people to react faster, but by building systems that fail less, recover automatically, and improve continuously. That is the foundation. Now let us understand how SRE relates to DevOps. One of the most common questions in this field is, what is the difference between SRE and DevOps? The honest answer is that they are complementary, not competing. DevOps is a philosophy, a cultural movement that breaks down the wall between development and operations teams. It says developers and operations engineers should share ownership, share tools, and work together toward the same goal. SRE is an implementation of that philosophy. It is the specific set of practices, metrics, and engineering disciplines that make the DevOps vision real. Think of it this way. DevOps tells you what to do. SRE tells you how to do it. Where they overlap, shared ownership, automation, continuous improvement, measurement, that is the heart of modern engineering culture. And when you add AI into that overlap, you get something even more powerful. But before we get there, let us understand the business case for why organizations invest in SRE in the first place. Site reliability engineering sits at the intersection of two disciplines that have historically been separate: software engineering and systems engineering. Software engineers build features. Systems engineers keep infrastructure running. SRE says those two things are not separate concerns. They are the same concern. Reliability is a feature. It has to be designed in from the start, not bolted on after the fact. When you combine software engineering rigor with systems engineering depth, you get a team that can build systems that are both functional and durable. And when you measure the output of that combination, using availability metrics, latency targets, and error rates, you get reliability as a quantifiable engineering outcome. That is the core of what SRE is as a discipline. Now let us look at why organizations actually invest in building it. The business case for SRE is straightforward. The cost of unreliability is enormous, and the investment in SRE consistently delivers measurable returns. On the cost side, downtime costs money, customer trust, and competitive position. On the benefit side, SRE reduces mean time to recovery, increases deployment frequency, reduces change failure rates, and frees engineering capacity from reactive firefighting to proactive improvement. The DORA research program, which has surveyed tens of thousands of engineering teams, consistently shows that high-performing organizations deploy code more frequently, recover from failures faster, and have significantly lower change failure rates than low performers. Those are not soft metrics. They translate directly to revenue, customer retention, and engineering velocity. The question is not whether your organization can afford to invest in SRE. The question is whether it can afford not to. With that foundation established, let us look at the framework that makes SRE work, starting with the Dickerson hierarchy of reliability. The Dickerson hierarchy of reliability is one of the most important frameworks in SRE. It was created by Mike Dickerson, who led the rescue of the healthcare.gov website in 2013, one of the most high-profile reliability failures in government technology history. The hierarchy works like Maslow's pyramid. You cannot address higher-level concerns until the lower-level foundations are solid. At the base is monitoring. If you cannot see what your system is doing, nothing else matters. You cannot respond to incidents you cannot detect. Above monitoring is incident response, the ability to react quickly and effectively when things go wrong. Then comes postmortems and root cause analysis, learning from failures so they do not repeat. Then testing and release engineering, ensuring that changes do not introduce new failures. Then capacity planning, ensuring your system can handle the load it will face. And at the top is product development, the ability to ship new features reliably and continuously. Every organization needs to build from the bottom up. And today, observability has replaced simple monitoring at the base. Because in complex distributed systems, you need more than dashboards. You need the ability to ask arbitrary questions about your system's behavior. We will cover that in depth shortly. SRE is built on 6 core principles that define how practitioners think and work. First, reliability is a feature. It is not an afterthought. It must be designed in from the beginning. Second, reduce toil. Toil is manual, repetitive, automatable work that does not produce lasting value. Every hour spent on toil is an hour not spent improving the system. Third, anticipate failure. Do not wait for systems to break. Design for failure, test failure, and build recovery into the architecture. Fourth, blameless culture. When incidents happen, the goal is to understand the system failure, not to punish the individual. Blame stops learning. Blameless postmortems accelerate it. Fifth, service level awareness. Every reliability decision should be grounded in explicit service level objectives, the commitments you make to your users. And sixth, shared ownership. Reliability is not the operations team's problem. It is everyone's problem. Developers, SREs, and product teams share accountability for the systems they build and run. These 6 principles are not just philosophy, they are the operating system for a high-performing engineering organization. Now let us look at the 5 pillar focus areas that translate these principles into practice. The 5 pillar focus areas of SRE define where engineering effort is concentrated to achieve reliability at scale. The first pillar is observability, the ability to understand the internal state of your system from its external outputs. Without observability, you are flying blind. The second pillar is efficiency, doing more with less, eliminating waste, reducing toil, and ensuring that engineering capacity is directed toward high-value work. The third pillar is resiliency, designing systems that degrade gracefully, recover automatically, and maintain acceptable service levels even when components fail. The fourth pillar is operational excellence, the continuous improvement of processes, runbooks, on-call practices, and incident response. And the fifth pillar is automation, replacing manual, error-prone human tasks with reliable, repeatable, automated processes. These 5 pillars work together. Observability tells you what is happening. Efficiency ensures you have the capacity to act. Resiliency limits the blast radius of failures. Operational excellence ensures your response is consistent. And automation scales all of it beyond what any team of humans could do manually. Now let us look at how SRE measures success, starting with the YBYO model. YBYO stands for You Build It, You Own It, You Operate It. It is a cultural and operational model that places end-to-end accountability with the team that builds the service. In traditional organizations, developers build software and throw it over the wall to operations. Operations runs it. When something breaks, there is a blame game. YBYO eliminates that wall entirely. The squad that builds the service is also responsible for its reliability, its on-call rotation, and its incident response. This creates a powerful incentive alignment. When developers are on call for the systems they build, they write more reliable code. They instrument their services properly. They care about error rates and latency because those metrics wake them up at night. YBYO does not mean every developer is a full SRE. It means that reliability is a shared responsibility, and the team closest to the code is also closest to the operational reality of running it. This model is foundational to how modern engineering organizations scale reliability without scaling headcount. Now, let us look at how we measure that reliability with SLIs, SLOs, and SLAs. The SLX framework is how SRE makes reliability measurable. Let me break down each component. An SLI, service level indicator, is a specific quantitative measure of service behavior. It is the raw signal. For example, the percentage of HTTP requests that return a successful response within 200 milliseconds. An SLO, service level objective, is the target you set for that indicator. For example, 99.9% of requests should succeed within 200 milliseconds, measured over a rolling 30-day window. The SLO is your internal reliability commitment, the standard your team holds itself to. An SLA, service level agreement, is the contractual commitment you make to your customers. It is typically set below the SLO because you need a buffer between your internal target and the promise you make externally. If you breach your SLO, you have an engineering problem. If you breach your SLA, you have a legal and business problem. The SLX framework turns reliability from a vague aspiration into a precise engineering target. It gives every team a shared language for discussing risk, prioritizing work, and making trade-off decisions. And it connects directly to the concept of error budgets, which we will cover next. The error budget is one of the most powerful concepts in SRE. Here is the core idea. If your SLO is 99.9% availability, That means you are allowed 0.1% unavailability. Over a 30-day month, that works out to approximately 43 minutes of allowable downtime. That 43 minutes is your error budget. It is not a failure target. It is a risk allowance. It gives your team explicit permission to take risks, ship new features, and run experiments, as long as you stay within budget. When the budget is healthy, you can move fast. When the budget is nearly exhausted, you slow down. You stop new deployments, focus on reliability work, and protect the remaining budget. This creates a rational, data-driven conversation between product teams and SRE teams about risk. Instead of arguing about whether a deployment is safe, you look at the error budget. The budget makes the decision. It is objective, it is shared, and it removes the politics from reliability trade-offs. Error budgets are the mechanism that makes SRE a business-aligned discipline, not just a technical one. Now let us look at what we actually measure to track that budget, the 4 golden signals. The Google SRE book identifies 4 golden signals that every service should measure. These are the minimum viable observability signals for any production system. The first is latency, how long it takes to service a request. Not just average latency, but the tail latency, the 95th and 99th percentile, because the slowest requests are often the most important ones to fix. The second is traffic, the demand being placed on your system. Requests per second, transactions per minute, active connections. Traffic tells you the scale of the problem when something goes wrong. The third is errors, the rate of requests that fail. This includes explicit failures, like HTTP 500 errors, and implicit failures, like requests that succeed but return wrong data. The fourth is saturation, how full your service is. CPU utilization, memory pressure, disk I/O, network bandwidth. Saturation is a leading indicator. When a resource approaches its limit, degradation is coming. If you instrument nothing else, instrument these 4 signals. They will tell you when something is wrong, how bad it is, and where to look. Now let us go deeper into how we observe these signals, and why observability is fundamentally different from traditional monitoring. Traditional monitoring asks, is the system up? Is CPU above 80%? Did the health check pass? These are known unknowns. You define the checks in advance, and the system tells you whether those specific conditions are met. Observability asks a different question. What is the system doing, and why? Observability is the ability to understand the internal state of a system from its external outputs, without having to define in advance every possible failure mode. In modern distributed systems, microservices, containers, serverless functions, failures are often novel. They emerge from the interaction of components in ways that no one anticipated. A monitoring dashboard cannot catch what it was not designed to look for. Observability can, because it gives you the raw data, logs, metrics, and traces to ask arbitrary questions about system behavior in real time. The shift from monitoring to observability is not just a tooling change. It is a philosophical change in how you think about understanding complex systems. And it is the foundation of everything that AIOps and AI-driven operations are built on. Let us look at the 3 pillars that make observability possible. Observability rests on 3 data types, and each one answers a different question about your system. Logs answer the question, what happened? A log is a time-stamped record of a discrete event. A user logged in. A payment failed. A service threw an exception. Logs are the most detailed signal you have, but they are also the most expensive to store and the hardest to query at scale. Metrics answer the question, how is the system performing right now? A metric is a numeric measurement sampled over time. CPU utilization at 73%. Request rate at 4,200 per second. Error rate at 0.02%. Metrics are cheap to store and fast to query, but they lose the detail of individual events. Traces answer the question, where did the time go? A trace follows a single request as it travels through every service in a distributed system.
It shows you exactly which service added latency, which database query was slow, and where the bottleneck lives. Together, logs, metrics, and traces give you a complete picture of system behavior. And the technology that makes it possible to collect all three in a standardized, vendor-neutral way is OpenTelemetry, which we will cover next.
OpenTelemetry is the most important observability standard in the industry today. It is an open-source, vendor-neutral framework for collecting and exporting telemetry data, logs, metrics, and traces from any application, in any language, running on any infrastructure. Before OpenTelemetry, every observability vendor had its own SDK, its own agent, and its own data format. Switching from one platform to another meant re-instrumenting your entire application. OpenTelemetry solves that problem. You instrument your application once using the OpenTelemetry SDK. The OpenTelemetry collector receives that data, processes it, and exports it to any backend you choose: Splunk, Dynatrace, Prometheus, Grafana, or any other platform. Your instrumentation code never changes, regardless of which backend you use. OpenTelemetry is now a graduated project under the Cloud Native Computing Foundation, and it is supported by every major cloud provider and observability vendor. For any organization building a modern observability practice, OpenTelemetry is not optional. It is the foundation. Now, let us look at what happens when you add artificial intelligence to this observability foundation, and how AIOps is transforming the SRE role.
This is a pivotal moment in the video. The shift to AI. AIOps, artificial intelligence for IT operations, is the application of machine learning and AI to automate and enhance IT operations. It is not a replacement for SRE. It is an amplifier. Traditional operations is reactive. An alert fires, an engineer investigates, a fix is applied. AIOps moves that model through 4 stages of maturity. At stage 1, you have reactive operations. Manual everything. Alerts are noise, and humans are the only decision makers. At stage 2, you have assisted operations. AI helps correlate alerts, reduce noise, and surface the most important signals. At stage 3, you have augmented operations. AI recommends actions, predicts failures before they occur, and automates routine remediation. At stage 4, you have autonomous operations. AI detects, diagnoses, and resolves incidents with minimal human intervention. Most organizations today are between stage 1 and stage 2. The leading organizations are pushing into stage 3. Stage 4 is the horizon, and it is closer than most people think. The SRE who understands how to design systems for AIOps, instrument them for AI-driven analysis, and work alongside autonomous agents will be the most valuable engineer in any organization. Let us look at the specific role that generative AI is playing right now. Generative AI is not a future technology for SRE. It is being used in production today, and the use cases are expanding rapidly. Let me walk you through the 6 most impactful applications. First, automated runbook generation. Large language models can analyze incident history, system topology, and past resolutions to generate step-by-step runbooks for new failure patterns in seconds. Second, intelligent alert triage. AI models can correlate thousands of alerts, suppress noise, and surface the 3 alerts that actually matter before a human would even open their laptop. Third, natural language log analysis. Instead of writing complex queries, an SRE can ask in plain English, "Show me all errors related to the payment service in the last hour." The AI translates that into a precise query and returns the results. Fourth, predictive failure detection. Machine learning models trained on historical telemetry can identify anomalies and predict failures hours before they occur, giving teams time to act proactively. Fifth, automated post-mortem drafting. AI can analyze the timeline of an incident, correlate the relevant signals, and produce a first draft post-mortem in minutes, reducing the cognitive load on engineers who just survived a major outage. And sixth,
AI-assisted capacity planning. Models can forecast traffic growth, identify resource constraints, and recommend scaling actions before saturation becomes a crisis. This is not science fiction. These capabilities exist today, and the SREs who know how to leverage them will define the next generation of the discipline. Now, let us talk about one of the most important concepts in SRE practice: toil.
Toil is the enemy of engineering. In SRE, toil has a specific definition. It is work that is manual, repetitive, automatable, tactical, and devoid of enduring value. Restarting a service every Monday morning because it leaks memory. Manually rotating credentials on a schedule. Copying and pasting data between systems because no integration exists. Responding to the same alert for the 6th time this month. Every hour your team spends on toil is an hour not spent making the system better. And toil compounds. The more toil you accept, the more toil you accumulate. It is a trap. The Google SRE model sets a hard limit. No more than 50% of an SRE's time should be spent on toil. If it exceeds that threshold, it is a signal that something is wrong with the system, and the team should stop and fix it. The antidote to toil is automation. And increasingly, AI is the most powerful automation tool available. When an AI agent can handle the routine, the repetitive, and the predictable, your engineers can focus on the work that actually requires human judgment. Now, let us look at what happens when toil is not eliminated fast enough. Incidents. Every incident follows a life cycle, and understanding that life cycle is critical to managing it effectively. The 6 stages are detect, triage, respond, mitigate, resolve, and learn. Detection is the first challenge. The faster you detect an incident, the smaller its impact. This is where observability, alerting, and AIOps earn their value. Triage is the process of understanding what is happening and how severe it is. Is this a P1 that requires immediate escalation, or a P3 that can wait until morning? Respond is the mobilization phase, assembling the right people, establishing an incident commander, and opening a communication channel. Mitigation is the immediate action to reduce user impact, even before the root cause is understood. Roll back a deployment, redirect traffic, increase capacity. Resolve is the full fix, addressing the root cause and restoring normal service. And learn is the most important stage that most organizations skip. The blameless postmortem, the retrospective, the action items that prevent the incident from recurring. AIOps is transforming the first 3 stages, detect, triage, and respond, by automating correlation, reducing noise, and accelerating the time from alert to action. The last stage, learn, is where generative AI is beginning to make its mark. Let us talk about that next. The blameless postmortem is one of the most powerful cultural tools in SRE. When an incident occurs, the instinct in many organizations is to find someone to blame. Who pushed the bad deployment? Who missed the alert? Who made the wrong call? Blame feels satisfying in the moment, but it is catastrophically counterproductive. When engineers fear blame, they hide mistakes. They avoid taking risks. They stop sharing information during incidents. And the same failures repeat because the systemic causes were never addressed. The blameless postmortem takes a different approach. It assumes that every engineer who was involved in an incident was acting with the best intentions and the best information available to them at the time. The goal is not to find the guilty party. The goal is to understand the system conditions that made the failure possible and to fix those conditions. A good postmortem documents the timeline, the contributing factors, the impact, and most importantly, the action items that will prevent recurrence. It is a learning document, not a punishment document. Organizations that do this well get better over time. Organizations that assign blame get worse. The choice is that simple. Now let us look at how organizations measure their overall SRE maturity. The SRE maturity model describes 4 stages of organizational evolution in reliability engineering. Stage 1 is reactive. The organization responds to incidents after they occur. There are no SLOs. On-call is chaotic. Postmortems are rare or blame-focused. Most organizations start here. Stage 2 is proactive. The organization has defined SLOs, established on-call rotations, and begun automating common remediation tasks. Incidents are tracked and postmortems are conducted. This is where many organizations plateau. Stage 3 is predictive. The organization uses observability data and machine learning to detect anomalies before they become incidents. Error budgets drive prioritization. Chaos engineering is practiced. Toil is actively measured and reduced. Stage 4 is cognitive. This is the AI-native SRE organization. AI agents handle routine incident triage and remediation autonomously. Generative AI assists with postmortems, runbook generation, and capacity planning. The SRE team's role shifts from firefighting to system design and AI oversight. Here's the question I want you to sit with. Where is your organization on this model right now? And more importantly, what would it take to move to the next stage? That question is the starting point for every SRE transformation. Now let us look at the tools that make this transformation possible.
The modern SRE toolchain spans 6 categories, and knowing these tools is essential for any practitioner. For observability, the dominant platforms are Splunk for log analysis and security intelligence, Dynatrace for full-stack APM with AI-powered root cause analysis, Prometheus for metrics collection in cloud-native environments, and Grafana for visualization and dashboarding. For incident management, PagerDuty and OpsGenie handle alerting and on-call scheduling. For infrastructure and automation, Terraform manages infrastructure as code, Ansible handles configuration management, and Kubernetes orchestrates containerized workloads. For CI/CD and release engineering, GitHub Actions, Jenkins, and Argo CD enable continuous delivery pipelines. For chaos engineering, Chaos Monkey and Litmus Chaos provide controlled failure injection. And for AIOps, platforms like Dynatrace Davis AI, IBM Watson AIOps, and Big Panda provide AI-driven event correlation and autonomous remediation. You do not need to master all of these tools immediately, but you need to understand what each category does and why it matters. In the videos that follow this one, we will go hands-on with Splunk, Dynatrace, Prometheus, and Grafana, the 4 platforms at the core of the observability practice. Now let us continue building the foundation.
Chaos engineering sounds counterintuitive. You are deliberately breaking your own production systems, on purpose. Why would any rational engineer do that? Because the alternative is worse. If you do not test your system's failure modes in a controlled way, you will discover them in an uncontrolled way, at the worst possible moment with the maximum possible impact. Chaos engineering, pioneered by Netflix with their Chaos Monkey tool, is the practice of deliberately injecting failures into a system to verify that it behaves as expected under adverse conditions. The methodology has 4 steps. First, define a steady state. What does normal look like? Second, hypothesize. What do you expect to happen when this specific failure occurs? Third, introduce the failure. Terminate an instance, inject latency, drop network packets. Fourth, observe. Did the system behave as expected? Did it degrade gracefully? Did it recover automatically? If the answer is yes, you have increased your confidence in the system's resilience. If the answer is no, you have found a gap, and you found it safely before a real incident exposed it. Chaos engineering is not for organizations that are afraid of failure. It is for organizations that are serious about reliability. Now let us look at another proactive discipline, capacity planning.
Capacity planning is the practice of ensuring that your system has the resources it needs to handle the load it will face before that load arrives. It sounds obvious, but in practice, most organizations discover capacity problems reactively. The system slows down, alerts fire, and engineers scramble to add resources under pressure. Effective capacity planning has 3 components. First, understand your current resource utilization. How much CPU, memory, storage, and network bandwidth are you using today,
and how is that trending over time? Second, forecast future demand. Based on business growth projections, seasonal patterns, and planned feature launches, how much load will the system need to handle in the next 30, 90, and 180 days? Third, identify the constraints. Which resource will hit its limit first? What is the lead time to provision additional capacity? What is the cost of over-provisioning versus the cost of under-provisioning? AI is transforming capacity planning by enabling more accurate demand forecasting, automated scaling recommendations, and anomaly detection that identifies unexpected growth patterns before they become capacity crises. The goal is to never be surprised by scale. Now, let us talk about the human side of SRE operations, on-call culture.
On-call is one of the most human aspects of SRE, and it is also one of the most abused. In unhealthy on-call cultures, engineers are paged constantly. Alerts are noisy and low quality, and being on call means chronic sleep deprivation and burnout. Engineers dread their rotation. Turnover is high. Reliability suffers because exhausted engineers make mistakes. Healthy on-call culture looks completely different. Alerts are meaningful. Every page represents a real, actionable issue that requires human judgment. Alert fatigue is actively measured and addressed. On-call rotations are fair, with adequate recovery time between shifts. Runbooks exist for every common failure scenario, and the on-call engineer has the tools, the access, and the authority to resolve issues without waiting for approval. The goal is not to eliminate on-call. The goal is to make on-call sustainable. AIOps is a critical enabler here. When AI handles the noise, the low-priority alerts, the routine remediations, the false positives, the human on-call engineer is only paged for situations that genuinely require human judgment. That is the on-call experience that retains great engineers. Now, let us look at how reliable software gets delivered in the first place: CI/CD and release engineering. Continuous integration and continuous delivery, CI/CD, is the engineering practice that enables organizations to ship software reliably and frequently. CI is the practice of automatically building and testing every code change as it is committed. If a change breaks a test, the pipeline stops and the developer is notified immediately, before the broken code reaches production. CD is the practice of automatically deploying validated changes through a series of environments: development, staging, production, with automated gates at each stage. The result is a deployment pipeline that can move code from a developer's laptop to production in minutes, with high confidence that it will not break anything. Two release engineering techniques are particularly important for SRE. Canary deployments route a small percentage of traffic, say 1%, to the new version of a service before rolling it out fully. If the Canary shows elevated error rates or latency, the deployment is automatically rolled back. Feature flags allow new functionality to be deployed to production in a disabled state, then enabled for specific user segments without a new deployment. Together, these techniques dramatically reduce the blast radius of any individual change. The DORA research shows that high-performing organizations deploy to production multiple times per day, with lower change failure rates than organizations that deploy monthly. Frequency and reliability are not in tension. They are correlated. Now let us look at runbooks and automation. A runbook is a documented procedure for responding to a specific operational event. When service X goes down, do these steps. When disk utilization exceeds 90%, do these steps. Runbooks are the institutional knowledge of your operations team, written down so that any engineer at any hour can respond effectively without having to improvise. Manual runbooks are better than no runbooks, but they have a ceiling. A human following a manual runbook takes 30 to 45 minutes to complete a complex remediation procedure. They can make mistakes. They can miss steps. They get tired at 3 a.m. Automated runbooks, executed by a script, a workflow engine, or an AI agent, can complete the same procedure in under 3 minutes, every time, without error, without fatigue. The progression is, first, document the runbook, then automate it. Then let AI execute it autonomously when the triggering condition is detected. This is the Toil elimination flywheel.
Every runbook you automate is one less page that wakes up a human, one less opportunity for human error under pressure, one more step toward the autonomous operations model. Now let us look at the metrics that measure whether all of this is working. DORA.
The DORA metrics from the DevOps Research and Assessment Program are the industry standard for measuring software delivery and operational performance. There are 4 metrics. Deployment frequency. How often does your organization deploy code to production? High performers deploy multiple times per day. Low performers deploy monthly or less frequently. Lead time for changes. How long does it take for a committed code change to reach production? High performers measure this in hours. Low performers measure it in weeks or months. Change failure rate. What percentage of deployments cause a production incident that requires a hotfix or rollback? High performers are below 15%. Low performers are above 45%. And mean time to recovery. When a production incident occurs, how long does it take to restore service? High performers recover in under 1 hour. Low performers take days. These 4 metrics tell you everything about the health of your software delivery system. They are not vanity metrics. They are predictive of business outcomes. Organizations in the top quartile on DORA metrics have significantly higher revenue growth, customer satisfaction, and employee retention than those in the bottom quartile. If you are not measuring these 4 metrics today, start tomorrow. Now, let us look at the architectural context in which modern SRE operates: microservices and the service mesh. The shift from monolithic applications to microservices architecture has been one of the defining trends in enterprise software over the past decade. A monolith is a single, large application where all components are tightly coupled and deployed together. Microservices decompose that application into dozens or hundreds of small, independent services, each responsible for a specific business capability, each deployable independently. The benefits are real: faster development, independent scaling, technology flexibility, and smaller blast radius for individual failures. But the operational complexity is dramatically higher. In a monolith, a request is a function call. In a microservices architecture, that same request might traverse 15 different services, each with its own database, its own failure modes, and its own latency profile. This is where the service mesh comes in. A service mesh, implemented by tools like Istio, Linkerd, or Consul, provides a dedicated infrastructure layer for service-to-service communication. It handles traffic management, mutual TLS encryption, load balancing, circuit breaking, and critically for SRE, distributed tracing. The service mesh makes the invisible visible. It turns the chaotic web of service interactions into observable, controllable, policy-governed communication. For an SRE operating in a microservices environment, the service mesh is not optional. It is the foundation of operational control. Now let us look at the platform that orchestrates all of these services: Kubernetes. Kubernetes has become the operating system of the cloud-native world. It is the platform that orchestrates containerized workloads at scale, and it has profound implications for how SRE is practiced. At its core, Kubernetes manages the deployment, scaling, and operation of containerized applications across a cluster of machines. The control plane, consisting of the API server, the scheduler, and etc., makes decisions about where to run workloads and how to maintain desired state. Worker nodes execute those workloads as pods, the smallest deployable unit in Kubernetes. For SRE, Kubernetes provides 3 capabilities that are transformative: self-healing. If a pod fails, Kubernetes automatically restarts it. If a node fails, Kubernetes reschedules the affected pods to healthy nodes. This is reliability built into the infrastructure. Autoscaling. The horizontal pod autoscaler can automatically increase or decrease the number of pod replicas based on CPU utilization, memory pressure, or custom metrics. This is capacity management that responds in real time. Rolling updates. Kubernetes can deploy new versions of a service gradually, monitoring health at each step and automatically rolling back if the new version fails health checks. This is zero downtime deployment by default. Kubernetes does not eliminate the need for SRE expertise. It elevates it.
The SRE who understands Kubernetes deeply can design systems that are resilient, scalable, and self-managing at a level that was simply not possible 5 years ago. Now let us look at how AI is reshaping the SRE role itself.
There is a conversation happening in the industry right now about whether AI will replace SREs. I want to address it directly. The answer is no, but the role is changing, and the engineers who understand that change will thrive. AI is exceptionally good at pattern recognition, speed, and scale. It can process millions of log lines in seconds, correlate signals across hundreds of services simultaneously, and execute remediation procedures without fatigue. What AI cannot do is exercise judgment in novel situations. It cannot understand the business context behind a decision. It cannot communicate with a panicked executive during a major outage. It cannot design the architecture that makes a system resilient in the first place. The future SRE is not competing with AI. The future SRE is directing it. They design the systems that AI monitors. They define the runbooks that AI executes. They review the postmortems that AI drafts. They make the judgment calls that AI escalates. The partnership between human SRE expertise and AI capability produces outcomes that neither could achieve alone: faster detection, faster resolution, higher reliability, and less burnout. The engineers who embrace this partnership now will be the most valuable practitioners in the field for the next decade. Now let us look at the career path that leads there. The SRE career path is one of the most rewarding in technology, both intellectually and financially. Let me walk you through the progression. At the junior SRE level, you are learning the fundamentals: on-call rotations, runbook execution, monitoring basics, and incident response. This is where you build the operational intuition that everything else depends on. At the SRE engineer level, you are owning SLOs, building automation, and leading incident response. You are starting to influence architecture decisions and drive reliability improvements. At the senior SRE level, you are designing systems for reliability, running chaos engineering programs, and integrating AIOps tooling. You are the person the team looks to when the hard problems arrive. At the staff SRE level, you are setting platform strategy, establishing reliability standards across multiple teams, and mentoring the next generation of practitioners. And at the principal or SRE manager level, you are defining the vision for reliability across the organization, aligning engineering culture with business objectives, and building the teams that build the future. Compensation reflects this progression. Junior SREs typically earn between $120,000 and $160,000. Senior SREs and staff SREs command $180,000 to $250,000. Principal and management roles at top-tier organizations can exceed $280,000 in total compensation. The skills that accelerate this path: Python and Go for automation, Kubernetes for infrastructure, deep observability expertise, and increasingly, the ability to design and operate AI-augmented systems. Now, let us see what this looks like in the real world. Let me show you SRE in practice through 3 organizations that have defined the discipline. Google invented SRE in 2003 because their search infrastructure was growing faster than their ability to operate it reliably. The solution? Error budgets, SLOs, and a dedicated SRE function became the blueprint for the entire industry. Today, Google Search maintains 99.99% availability across billions of daily queries. SRE is not just a team at Google, it is the operating model for the entire company. Netflix faced a different challenge: streaming video to over 200 million subscribers simultaneously, with zero tolerance for the kind of outage that would send users to a competitor. Their solution was radical: build systems that assume failure is inevitable and design for graceful degradation. Chaos Monkey, which randomly terminates production instances, was not a testing tool, it was a cultural statement. We are serious about resilience. The result is 99.97% availability for one of the world's most demanding streaming platforms.
Amazon built AWS on the premise that it must be the most reliable cloud infrastructure on Earth, because every customer who runs on AWS is trusting Amazon with their own reliability. Cell-based architecture, game day exercises, and automated remediation at scale have produced the industry-leading SLAs that make AWS a $90 billion business. The common thread across all three: reliability is not an accident. It is an engineering outcome, and it is achievable. Now, let us bring this all together.
Let me leave you with 6 takeaways from this video. First, SRE is a discipline, not a job title. It is a way of thinking about reliability as an engineering problem, one that can be measured, designed for, and continuously improved. Second, measure everything. SLIs, SLOs, error budgets, and DORA metrics are your compass. Without measurement, you are guessing. Third, observe. Do not just monitor. Logs, metrics, and traces together give you the ability to understand your system's behavior, not just whether it is up or down. Fourth, automate toil away. Every manual task is a debt. Runbooks and automation pay it down. The goal is to free your engineers for work that requires human judgment. Fifth, embrace failure. Error budgets, chaos engineering, and blameless postmortems are not signs of weakness. They are the practices that build the most resilient systems in the world. And sixth, AI is your partner. AIOps and generative AI amplify every SRE capability. The engineers who learn to leverage them now will define the next generation of the discipline. These 6 principles are your foundation. Everything else we cover in this series builds on them. Let us look at what comes next. That is the complete foundation of SRE and AIOps. In the next video, we go deep on observability, hands-on with Splunk, Dynatrace, Prometheus, and Grafana. You will see exactly how these platforms work, what they look like in a real enterprise environment, and how AI is being built into each of them. If this video gave you value, subscribe and turn on notifications so you do not miss it. Drop a comment below. Where is your organization on the SRE maturity model? I read every comment, and your answer might shape what we cover in a future video. And if you know an engineer who needs to see this, share it with them. The more practitioners who understand this foundation, the better the industry gets for all of us. I will see you in the next one. Thank you for watching. If you found this valuable, please connect with Juan on LinkedIn and subscribe to Next Gen AI for future next generation technology lectures.